Okay. So, this is what a light wave does to an atom. It drives it, displaces electron clouds, that motion is oscillatory at the same frequency as the driving field. The driving field can either be have a frequency less than the natural frequency or the resonant frequency of the atomic system or matter, or it could have a frequency greater than the natural frequency omega naught of the system, or it could be at resonance when both are equal. So, this sort of brings this question to closure, what does light do to matter? But now, but we are not just interested in that, the story completes when we understand that light having done something to matter, how does matter give back? Okay. So, what does an atom do to the light wave? This question is important. So, let us use the remaining 10 minutes of the class to answer this question in part or full. Now, we are in this game where we are skeptical about everything and want to go and open up the thing to its nuts and bolts and look threadbare into what's going on inside. That's the game, or that's the scenario we have walked into. So, let us do that in style. So, we want to now figure out what matter does to light. We know how light affects matter. Okay. So, let us take a piece of a medium being the key word, and an electric field, time dependent electric field E of t is incident. Okay. So, E is a function of x, y, z and t if I use the Cartesian coordinate system, but here I am using a one dimensional model. Okay. The light wave is propagating only in the z direction, the propagation direction is z. Therefore, the electric field has to oscillate along x or y, does not matter what it is, it is consider a linearly polarized wave, okay, for simplicity, and also it without any loss in generality, if I may say so. Then we need only one spatial variable z. If I know the input of the electromagnetic wave going into a medium at E of 0 t entering into a medium, at the output of the medium which has a length L, if after propagating a distance L in this medium, which again I am making some simplifying assumptions that the medium's response is linear, the medium is homogeneous, and I would toss in for this discussion's sake isotropic, but isotropy is not so much of our concern in this case, because it is we are considering a one dimensional model. So, there is anyway only one direction, but the linearity in the medium, okay, and the homogeneity of the medium are important considerations. Homogeneity in the sense every thin slice, as I have cut this medium into, is identical to any other. Okay. Considering this scenario, we want to figure out the output electric field at the end of the propagation, but then in order to do that, we would ideally want to figure out the electric field at any intermediate position of propagation inside this medium at any value of z, and hence also at z is equal to L. That is the approach we are going to take, right. Now, we already made the case that a part of the electromagnetic wave can be absorbed by a medium, not the entire wave in fact is not perfectly absorbed by any medium for that matter. In fact, making a perfect absorber is a challenging scientific problem, if one may even think about it in a more deep way. Therefore, the wave that is transmitted out at any point, not just transmitted out, the wave at any point in the medium or having passed through the medium has two pieces to it. One piece is obvious, okay, or one part of it is obvious, that is the incident wave itself is one part to it. The total field is a sum of the incident wave plus any wave that is emitted by the material medium and has some amplitude at a given point z. So, our attention is focused to a particular point z in the medium. The electromagnetic wave here is a sum of the incident field plus any emitted field in this medium. All right. So, Maxwell's equations will allow us to solve the total field which is on the left side, which is E of z t. Okay. They are differential equations. We need to know the initial condition well in order to solve them and propagate the wave forward in time and in this case in space too. So, E of, if we know E at z is equal to 0 and t, we will be able to figure out that at for any value of z. Okay. So, that is the philosophy of undertaking this this study. Okay. So, let us take this argument further. Okay. So, at every plane in the medium, light is excited by atoms. Light was passing through atoms, it oscillated the electron cloud. That oscillating electron cloud emitted light waves, okay, and the incident wave interfered with this emitted beam. There are two waves present in this in any medium when light is propagating to it through it. The amplitude of the emitted wave can be different from that of the exciting wave, if you wish, the incident wave, if you wish. Okay. The resulting wave, okay, then goes on to excite the atoms in the next plane. So, the idea is in a way simple. The light wave is incident on a material medium whose first slice I take, we take, and at the exit of this interaction, we have two waves, one emitted by the oscillation of the electron due to the incident electromagnetic wave. The other wave is essentially the other aspect is the incident field itself. Okay, I can imagine that this can appear to be confusing if you wish. Yeah, the point is, imagine an infinite steady state wave interacting with a medium. Do not think of a pulse, do not think of transients, think of steady state. Okay. So, what then would happen is that a field is set up everywhere. Okay. So, therefore, and the two aspects of the wave have come into some kind of, you can say, the system has come into equilibrium, and at any point going forward in this scenario, at any point going forward in this scenario, we have both these waves interacting with each other. Recall also that only a part of the wave can get, part of the incident wave could have gotten absorbed, okay, and a part of it goes unaffected, transmitted through the medium, okay. That is pretty much there, and these two waves must be summed up properly and coherently and so on, because there is only one source over here, okay. So, now the question we ask is, what will be the light's field at having propagated a distance, some distance z through this medium along the propagation axis, if this is 0. We want to solve this problem. Okay. So, if you do not if you think it is a puzzle that we are adding the incident field and the emitted field at every point in this case, consider this scenario of how polarizers work. Okay, I am considering this so called wire grid polarizer. Where an electromagnetic wave with random polarization, look at this, look at the polarization profile of the wave here, it is randomly polarized. Okay. The electric field vector is oscillating in all kinds of directions, in all kinds of planes. Now, when this is incident on a wire grid which goes in and out of the plane of the screen, which is a neat thing. What is a wire grid? It is a grid made up of straight line metallic wires which are very thin, okay, and which have a reasonable fill factor in this medium, and the gap between the wires is much smaller than the wavelength of light, okay, and the thickness of the wires is also much smaller than the wavelength of light. If the thickness of these wires and the gap between them, let me take these to be some t, this is much smaller than lambda. Why we force this to be much smaller than lambda is because we do not want diffraction, any diffraction effects, and basically diffraction is the phenomenon occurring when light encounters an edge and gap and so on. So, there are literally no gaps in that sense, and diffractive effects are negligible in this case. Then this is this element acts like a polarizer. It lets one of the two polarization components, in this case either the vertical, let us call it V, or the horizontal, to propagate through, ideally only one. Practical polarizers are different, we will not discuss that now. Now, note here the direction of the wire grids shown here and the polarization of the wave emerging out, the polarization that survives and gets transmitted through the polarizer. They are both orthogonal to each other. The wires are horizontal and the transmitted polarization is vertical. Now, since these are wires, and let us consider them to be very thin wires, so that these are one dimensional objects, right. These are in and out of the plane of the board. Electrons actually are oscillating in this direction, in the horizontal direction, whereas the polarization that is transmitted through is perpendicular to the direction of oscillation of the electrons. This is the principle of working of a wire grid polarizer, a polarizing element. Okay. So, why is that so? What is the logic behind this? Okay. The logic behind this is the fact that this polarizer works by the principle that as far as the wave propagating in the forward direction is concerned, the oscillating electrons which are oscillating in the horizontal direction emit a wave. So, there is an E emitted, there is an incident wave E incident, right. These two are out of phase by pi as we discussed, and they cancel each other out, whereas there is no oscillation in the vertical direction. There is no electron oscillation in the vertical direction. That component goes through unhindered. These two are out of phase by pi and they cancel out each other for the horizontal polarization. Okay. So, that is, you can say, evidence for the hypothesis that I am building. Okay. So, what matter does to light now needs to be put on a firm framework. We will do that and come back to it in the next lecture, and this is perhaps the most important view graph of this section. So, let me emphasize this. What matter does to light is captured in a few important relations. Maxwell's equations in a medium are 4. The Gauss law for electric fields, divergence of D is free charge density divided by epsilon naught in SI units. Divergence of B is always 0, Gauss law of magnetism always 0. Curl E is minus dB by dt, Faraday's law, and curl H is d I mean the time partial time derivative of the D field, okay, that we can say D dot in another notation, plus J free, we should have had a free over there. Okay, so, these are the 4 Maxwell's equations without any assumptions or compromises. So, complete classical electromagnetic theory. Okay, so, the point being that we now have 4 fields. The 4 fields here are D and E, H and B. In order to solve these, we have 4 equations, differential equations, 4 fields plus a scalar field here and a vector field here for free sources. So, we should know what the free sources are for solving these equations, but is that sufficient? Suppose I did not have any free sources, rho free and J free are 0. What if that is the case, do I have all the information just written in these 4 Maxwell's equations to solve them? Actually not, because I do not know the relationship between E and D. Who are these 4 guys, right? So, therein come the constitutive relations, which is another way of saying that E, D, H and B cannot always be the same irrespective of the medium in which the wave is propagating. These have to be, there has to be some material or medium specificity built into our electromagnetic wave plus matter in being put into the physical framework. So, that comes about by what we call constitutive relations, the relations that relate D to E, B to H. Epsilon naught is the permeability, no, it is the permittivity of free space. Mu naught is again a property of free space, right. So, these cannot be material specific or medium specific. Where does medium specific information get ingrained into this model? Medium specific information is ingrained in this model, and which is the model for electromagnetic waves interacting with matter in the Maxwell framework. It is in P and it is in M. Okay. Now, we had this whole discussion about what light does to matter and what matter does to light. Maxwell's equations knock off the free charges, you can convert this to the wave equation. They are going to very successfully describe the propagative phenomena, but material response is captured in the constitutive relations. That is where we need to fix everything, and that essentially is done at various levels of linearity or complexity if you wish. The most simple assumption I can make is that okay, E is the applied field, the field that primarily is present all over. If I removed my material medium and let the wave propagate through, it would have occupied in the same volume of space. The field that would have occupied the same volume of space would be E. So, E is for that volume of space being empty, whereas when I put some material there, we can consider, I mean the field that is actually present inside is effectively D when there is a medium present there. Okay. Now, D, the material field in the constitutive relations, is essentially a field containing two quantities. This is how we view it. The pristine field E plus another field P, which is called the, ironically the same a term that is doubly used here, called the polarization in the medium. What is polarization in the medium? It is for every point in the medium or else outside your medium of interest to everywhere, you compute the density of dipoles, local density of dipoles, here V being volume, local density of dipole moment per, this should also be a function of RT, it is the local dipole moment for per unit volume. Okay. This emerges out of careful considerations of classical electromagnetic theory, but the take home message is that this constitutive relation is what we need to take seriously take home and sleep over with tonight. Okay. Now, what is the relation of P to the input medium, if anything? We built this whole story about light creating oscillations of the electron cloud in matter and so on and so forth, right. So, that essentially is now going to play out in terms of its action. So, we will take this and go forward from this point in tomorrow's class. Okay. With that, I will pause here and stop. If you are tired and want to carry on, you are free to do so, but if you would like to have any discussions, we can do that. You can of course pause the recording as well.